colleague Feroz, we'll be discussing the affinity laws, pump power consumption and efficiency, adjusting the pump performance curve, as well as cavitation and MPSH. Thank you so much. Feroz, over to you.
Thank you, Stefan. Let me try to share my screen.
Just before you start, ladies and gentlemen, please make sure your microphones are muted so that we only listen to the presenters. Thank you, Feroz. You can proceed.
Thank you so much, Mr. Devo. Thank you, Stefan. It was a great introduction and then the topics covered. So let me continue from affinity laws. Hope everyone can see my screen.
Yes, at least here we can see your screen.
That's amazing. Let me also take my pointer. Yes, super. So affinity laws. Actually, when it comes to centrifugal pumps, actually we have a couple of laws, 3 laws basically, which are used especially when we need to change something, if we are using variable frequency drive up, or if we are trimming the impellers. When we have these situations, like when we oversize the pump, we need to adjust the speed or diameter of the impeller where possible. So we have to do these adjustments. So we have 3 different laws. So these laws basically help us to identify how flow rate, head of the pump, and power consumed by the pump are related to the speed of the pump or diameter of the impeller. So as you can read for yourself, the first one is the law one is flow versus speed or diameter. So the flow, which is Q, is actually directly proportional to the speed or diameter of the impeller. So from that perspective, Q1 by Q2 equal to N1 by N2 or D1 by D2, meaning we have a duty point 1 and duty point 2. So if we know the duty point 1, the flow rate of the point 1, and if we know the speed of point 1, and if we want to change the speed, we can calculate the flow at the point 2. Same goes for diameter. So if we know the flow rate at point 1 and then the corresponding diameter, we can find, if we trim the impeller, what will be the flow rate. And coming to the relation between head and speed, so the head of the pump is proportional to square of the speed. So from that perspective, so we have this formula, H1 by H2 equal to N1 by N2 or D1 by D2 to the power square. So here also, if we know the duty point before trimming or before changing the speed, then we can calculate what will be the head when we change the speed or diameter of the impeller. These are very straightforward formula. Then the last law is actually the relationship between power and speed or the diameter. So power is directly proportional to cube of speed or the diameter. So P1 by P2 is equal to N1 by N2 to the power cube or D1 by D2 cube. Now let's move on to the next topic. That's on pump power consumptions and efficiencies. So we have different efficiencies. We come across different efficiencies in pumps. So let's look at how we calculate those efficiencies and what are the different power consumptions we come across in pumps. So Stefan covered that a pump is a machine which helps to convert energy. Basically, pump is the part which converts mechanical energy to hydraulic energy. But before that, there is another machine used. That's the electric motor. So the electric motor converts electrical energy to mechanical energy. So we all know that, whenever there is a conversion of energy, we will be losing some energies in terms of losses. So that is related to the efficiency. Let's try to find how they are related. So in pump terminologies, we come across 4 different power terms. P1. P1 is the ultimate power that we consume. So P1 is the power consumed by the motor. It is the power that we pay for. We consume from the grid. So that is P1. So we give P1 to the motor. Then what happens? The motor converts energy. So we get P2 as the motor shaft power. So what we get out of the motor is P2. Then we give that power to the pump. That will be P3. You can argue P2 and P3, is it not the same? Actually, it is assumed to be same, but in theory, it is not same because we have something called coupling. So this P3 is after the coupling losses. So we have the power output from the motor and we have a coupling. And then after the coupling, we give the power to the pump. So there will be a little, very negligible power lost in the coupling. But for practical reasons, we can assume that P2 is equal to P3. Then finally, give P3 to the pump. And then we get P4 as the hydraulic output. So hope it's clear. So P1 is the input we give to the motor. P2 we get out of the motor. So there will be some losses in the motor. And how much will be lost? So that is based on the efficiency. And then we give P3 to the pump. We get P4 from the Thank you. Good. So from curve, what we get is actually P4. And then we have on the power curve, we will be having 2 curves, but in the picture that we are seeing now, we have the P2 curve. Okay. So we have seen 4 different power ratings, and we also come across one more thing that is called motor reserve power. So what is motor reserve power? So we have seen P2 is basically the power coming out from the motor, or that is what we give to the pump. But we cannot we cannot size the motor for that power. Whatever we consume, we cannot size. We need to size the motor with some reserve power. So how do we know how much we have reserve? So the reserve power is basically the difference between the rated of the motor and then the shaft output from the motor. So the difference between rated power and then shaft output is called the motor reserve we have in the motor. For example, if it is a 7.5 kilowatt motor, then if the motor is consuming, means the demand from the pump is say 6 kilowatt at the maximum load, then the difference between 7.5 and 6 kilowatt, so which is 1.5 kilowatt. So 1.5 kilowatt will be the motor reserve power. Now let's look at the different efficiencies that are involved in pumping application. So first one is the motor efficiency. So in motor, we have two powers. P1 is what we give to the motor and P2 is what we get from the motor. So theoretically, it cannot be the same. P1 and P2 cannot be the same. We will be having some losses in the motor. So that will be in the form of heat energy. So this is the formula that we use to calculate motor efficiency. So motor efficiency is equal to P2 divided by P1. So output divided by input. So that's the motor efficiency. Then coming to the pump, we have the hydraulic output. And we have also seen the formula when Stefan was presenting. So flow into H divided by 367. So that's the formula to calculate hydraulic output. So that will be calculated from the performance curves given by the pump manufacturers. So we know the Q, we know the head, so we can calculate the power required or the hydraulic output. So hydraulic output divided by power input, which means P4. P4 is our hydraulic output, and P3, or we can also consider for that matter P2, because we discussed P2 and P3 will more or less be the same. So P4 by P3, so that gives the pump efficiency. And if you want to know the overall efficiency, because P4 is the ultimate output of the pump and P1 is the ultimate input to the pump set. So if we divide these two, P4 divided by P1, then we will get the total efficiency. Or what we can do is we can multiply the motor efficiency and pump efficiency. So if we can multiply these two, motor efficiency and pump efficiency, we will also get total efficiency. For example, say motor is 90% efficient and the pump is say 70% efficient. So if we multiply 70 into 90, then we will get the total efficiency of the pump set, complete pump set. Then the next topic that we will discuss will be adjusting pump performances. Because when we have a pump or when we order a pump for a specific requirement, we cannot just get and use as it is. There could be a number of reasons why we need to adjust the pump. For example, while selecting the pump, we will consider some factor of safety. So we oversize the pump by 10%, 15%, or sometimes 20%. So when we install the pump, so the pump will be overperforming. So we may need to adjust the pump performance. This is a case number one. The other, for example, if we have a pump in a store, we want to use it for some standby requirement. So that pump may not be exactly fitting the requirement. So we may need to do some adjustments so that we can use that pump for the required application. So let's see what are the different ways we can adjust the pump to get what exactly we need. There are 4 methods used to adjust pump performance. Thank you. So first one is throttle control. So by having a valve and throttling, this is the most common methods we use to adjust the pressure or to reduce the flow rate. The second one is called bypass control. So where we cannot have a throttling valve and control the pump, so we need to have a bypass valve. And third one is impeller trimming. We have seen by trimming the impeller, we can control flow, head, and power requirement. So we can do impeller trimming. The last method, and I would say the most energy efficient and modern method, is by controlling the speed of the pump using variable frequency drive. So these are the 4 different methods we use to control pump performance. Now let's look at a little bit in detail of each of these methods. First one is throttling method. So throttling, what we do, so we have a system. So we are taking the pump, and we use a throttling valve on the discharge of the pump to control the pump performance. So let's look at what happens to the system when we have a throttling valve and control the valve. So what you see here is the pump performance curve. So this is the curve. So by this method, we don't change anything to the pump performance curve. Pump performance curve remains the same. And what you see here, this is the system curve. Basically, this is the static head and then the dynamic head. So when we change the frictional losses, so this dynamic head will change. So our original duty is this square, blue square. So this is our original duty. This is where the pump is operating now. So 60 meter cube per hour, and it is delivering 70 meters head. Now we are seeing we are getting more flow. We don't need 60 meter cube per hour. We need only 50 meter cube per hour. Then what we do, we throttle the valve. So when we throttle, what we are doing is we are increasing the system resistance. So when we increase the system resistance, the head will increase. So the duty point will move from this point to a newer point, and this will be our modified duty point. So at this point, our flow rate will be 50 meter cube per hour. On the other hand, if you look, we are increasing the head. So earlier it was 70 meters. Now we are increasing that to 76 meters. By this method, we are killing some energy, but the priority will be to meet the system requirement, which is the flow rate. So to meet the system requirement, so we may need to compromise on the efficiency a little bit. Then next method is bypass control. So in bypass control, what we do, in bypass control, we have the system, we are taking the water, and the water is going back to the system. Here we have a bypass valve. We take a bypass line and we install a valve on that line. Why not we have a valve on the discharge? Why not we do that? In some applications we cannot do, because when we are doing that, we are increasing the pressure. So in some applications we can't afford to increase the pressure, or the system will not allow us to increase the pressure beyond certain point. So in those applications, we use the bypass valve. So one of the examples is water treatment plant, in reverse osmosis plants. To meet certain requirement for the pump also, sometimes, for the pump also, we need to have a minimum flow. If the pump is operating too much on the left-hand side of the curve, is also not good for the pump. So in those cases, we use this bypass valve. Means we will have excess flow in the pump, but that excess flow will not go into the system, but that excess flow will come back to the pump. So for the pump, we meet the flow requirements, whereas for the system, again, we will let only the amount of water that is required for the system. Let's look at the system performance, how it differs. Again, the blue square one, the original duty point. So the pump is operating. So this is our static head. have the dynamic head, and our pump performance curve in this case all will not change. We will be changing only the system curve, as you can see here. So the pump is operating here. If we open the bypass valve, what will happen? There will be excess flow. So the some of the flow in the line will come back to the pump. So in this process, we are reducing the system resistance. We are increasing the flow, we are reducing the system resistance. So when we do this, the system curve will shift towards the right-hand side of the curve. So from this point, the duty point will move to a modified duty point. So in this case, we get excess flow, 81 meter cube per hour, but then system will get 60 meter cube per hour only as per the requirement. But the difference in the original duty point and the modified duty point, so this difference of 21 meter cube per hour, so that will be circulating in this line. So it will not go to the system. So we are not increasing the pressure. So the system will have reduced pressure and also reduced flow, means required flow. But the excess flow will be circulating in the line. And in this case also, we might have some energy getting killed in this process. We may have to compromise a little bit. Now let's look at the third method. So third method is by trimming the impeller. So if we trim the impeller, we are reducing the size of the impeller. When the size of the impeller reduces, we also reduce the performance of the pump. So if you notice in our previous two cases, we have not touched on the pump performance curve. Pump performance curve remained same. Only the system curve changed. But in this third method, what we are doing is when we trim the impeller, the performance of the pump, the curve will shift below, as you can see here. So this is the original pump performance. When we trim the impeller, this will be the new performance. So we are reducing the performance of the overall pump itself. Okay. And we have also seen in the affinity loss, so when we change the diameter, how the flow, head, and power changes. So using the affinity loss, we can calculate what will be the new performance. So if we have the duty point from the original curve, we know the flow, head, and then the speed. So if we know the our required flow head, then we can calculate the speed, or if we know the revised speed, then from that we can calculate what will be the newer flow and head, and also the power consumption. And impeller trimmings are mostly used for permanent where we are 100% sure that the duty, this will be the duty, we will not vary the duty. So in those cases, we can trim the impeller. Again, not all the pumps we can trim the impeller, only mostly the cast pumps in general of higher flow rate. So we trim the impellers. Then the last method is speed control. So this is the most, I can say, the modern method, because when we trim the impeller, if you want to go back to the previous duty point, it's not possible. We may need to change the complete impeller. So in this method, what we are doing is we are changing the pump performance, as you can see from the slide. So the pump performance will change from this to the lower performance curve. The advantage with speed control is if you want to go back, we can go back to the previous performance curve. So mostly speed control is used where we have a varying demand. So for example, municipal water supply. So in municipal water supply applications during peak hours in the morning or in the evening, we might need more flow. Off peak time, so we might need lesser flow rates. So we can use speed control to meet the demands. And in speed control, if you can see, we are not compromising on the efficiency. So the efficiency it means the power consumption will reduce substantially when we change the speed from this duty point to the newer duty point. So the power consumption will reduce substantially when we change the speed of the pump. So that's the great advantage of variable frequency drives. So in first two methods, we were playing with the system curve. We were increasing the system resistance or reducing the system resistance to control the pump performance. In the third and fourth method, so we are not touching the system curve. We are disturbing the performance curve of the pump by either trimming or by controlling the speed of the pump. Hope this part was clear. Then the last topic for today's session, cavitation and NPSH. This is one of the important topics when it comes to pumps, and also sometimes people a little bit struggle to understand these concepts. We will try to explain as simple as possible. And if you have any questions, we can discuss on your questions after the session, after the presentation. Sorry. What is cavitation? So cavitation occurs in a pump when the pressure on the suction side of the impeller falls below vapor pressure of the liquid. So basically what we are doing is when the pressure falls below vapor pressure, then the liquid will turn into vapor, which is not good for the pump. So there will be some air bubbles formed when the pressure falls below vapor pressure. So these air bubbles are like bullets. They're very implosive. You can see in this picture. So the cavitation can erode the material. So they are very powerful and they can erode the material. As you can see, these are real life pictures what cavitation can do.
Okay.
So the cavitation is not good for the pump. Cavitation results in increase in noise level, increase in vibration, which can damage bearings, pump bearings, and mechanical seals, etc. And they erode and damage the impellers. And also, cavitation will reduce pump performance. Let's look at how it happens theoretically. We'll go back to the previous slide. So A is basically the front of impeller vane, and B is back of impeller vane, as you can see from this picture. So A is front side of the impeller. Here, nothing will happen. This will be mostly this side will be under pressure, but the back side of impeller vane. So here is what the it will create some vacuum to pull the water. So when it happens, if the pressure drops below vapor pressure of the liquid, as you can see here, so the pressure will drop. Actually, it should go back from here. So if it drops to the vapor pressure, so here you can see the liquid will convert from the liquid will convert to vapor. Then air bubbles will be formed. So once air bubbles there, then the performance will suddenly drop. This is the original performance. And when the pump cavitates, the performance will suddenly drop. This is from impeller inlet to impeller outlet. So from the eye of the impeller to the impeller output, this is what will happen. This process will happen. Then how do we ensure that the pump is not cavitating? Here comes the concept called NPSH. So net positive suction head. Using this terminology, and there are some calculations behind that, so we can actually eliminate the risk of cavitation. In NPSH, we have two terminologies. One is NPSH is basically net positive suction head. So what is the suction head, net positive suction head? We will have, so again, we have two terminologies. One is NPSHR, which means how much is required by the pump to avoid cavitation. So that's called NPSHR. Who will provide this information? The pump manufacturer will provide this information. The second term is NPSHA. A means available. What is available at site? So this can be NPSHA will be calculated using formula. So when NPSHA means what is available at site is more than what is required by the pump, which means we are feeding more to the pump, then we eliminate the risk of cavitation. On the other hand, when NPSHA available is less than what is required by the pump, means the pump will starve. So in this case, cavitation will happen. First, let's look at how to find NPSHR. So this is, as I mentioned earlier, so this is published by the pump manufacturer. So we have the pump performance curve. So we have the flow and head curve, and this is the efficiency curve, the dark blue, and this one is the red one is the efficiency curve. And in the bottom, you can see two curves. One will be power consumption, P1, and also we will have P2. So those two will be parallel curves. On the bottom, what you see is the NPSH curve, so net positive suction head required curve. So if this is our duty point, so around 70 meter cube per hour at 42 meters, so we can go down and then see what is the NPSH required by this pump at this duty point. This is also, the NPSH also will vary from duty point to duty point. So if we go towards left-hand side, the NPSH will come down, requirement will come down, which is good for the pump. If we go towards right-hand side of the curve, as you see, the NPSH required will go up. Means we need to be very cautious and ensure that what is required being met. Anyways, we will see in the following slides how we calculate, how we mitigate the risk. But you can read from here. So in this case, you can see the NPSH required is 3 meters. These are the values. The NPSH required is 3 meters for this pump. So this is how you can identify, you can find the NPSH required details. These are based on the test data the pump manufacturer will publish. So let's look at how to calculate the available. So required will be given by the pump manufacturer, but the people who are at site or who are making the intent, so they will have to find what is available. This is the formula which is used to calculate net positive suction head available. HB is the atmospheric pressure, and HF is the frictional loss in suction pipes. So in the suction pipe, what is the frictional loss? HV is the vapor pressure of the liquid. So this vapor pressure depends on liquid temperature. When the temperature is high, then the vapor pressure value will be very less. So, and vice versa. Then HS is factor of safety. 0.5 to 1 meter is what is considered as best engineering practice. Then H is the maximum suction head, how much the pump can lift water. And we need to add if we have positive suction head. For example, if the water level is above the pump inlet level, if the tank is above the pump, then we need to add this data. We need to use plus. We need to subtract if it is a suction lift. Okay, so this net positive suction head data. So this is actually influenced by two factors. One is the temperature, and then the second one is elevation. So without doing anything on the calculation, if we change the temperature, if the liquid temperature changes, that will change the vapor pressure, and also the atmospheric pressure. So that again depends on the elevation. As you can see here, if the temperature of the liquid, if this changes, you can see the vapor pressure, how this will change. Temperature goes up, the vapor pressure also goes up. And then if the atmospheric pressure varies, then you can see the available NPSH available also varies here. This is basically calculated value. So for this temperature, we have this vapor pressure. Then we have the atmospheric pressure. Then we calculate. So as you can see, the available goes down when the liquid temperature goes up. Okay, if you are in municipal water supply, this may not affect a lot. But if you are working in a power plant and if you have a boiler, so you need to size pump for boiler feed application where the temperature will be around 100 degrees, then this can be really dangerous because available is 0. So it doesn't have any pressure at the pump inlet. So in this case, what we need to do is we need to provide positive suction head. And also in the second table, you will see the altitude, how the altitude changes the atmospheric pressure. If we go high, as in the case of mountains, we go up, then the atmospheric pressure available will come down. So this will affect performance. So we need to be very mindful of the altitude and liquid temperature when it comes to NPSH. I think that was the last slide. If we have any questions.
Thank you very much, Feroz. My colleague James was supposed to be taking us through the question and answer session. Feroz, Stephen, and Anthony from Grundfos. Thank you very much for the wonderful presentation. And I think you have also managed the time very well. I can see a lot of people are asking if the presentation will be shared. I think that is the first question. Anthony, if, not Anthony, but James, if you are around, please just let me know so that you proceed with your session. But the first question is it possible for the presentation to be shared to everyone? And I have picked a number. the IEK has also sent me. There are too many questions, so probably we will be choosing what can be answered in this session, and then the other way is to send to Grand Force the questions, and then they can answer them at their time. Anthony, are you around? I mean, James Kagut. Okay, fine. I'll share 5 questions that have been asked. Let the Grundfos team answer. If we have time, again, I'll share another set of 5. Again, I'm requesting, let us mute our microphones. So, question number 1, I've already said, will the presentation be shared? And then there's a member who did not understand how the bypass valve works. Another member wanted to know if Grundfos offers training to individuals, and if yes, what can he do to benefit from that training? Then there's the question of the difference between pumps in series and a multi-stage pump. And another member asked what is the difference in performance and efficiency between Grundfos pumps and Dayleaf and Pedrolo. I guess whoever will be answering can expand this, because now we have very many pumps. Anthony, I'm sure you can, if you've noted those 5 questions, you can assign them in your team who is to answer which. Then we'll do the next one. Thank you. Anthony, are you there?
Yes, I am. Yes, I am. I've noted the questions and I can also see them in the chat. I will answer regarding the presentation. I think together with IIK, we will make the presentation available. But then allow me to just allocate the other questions. I think Stefan will come back to us on the operation of the bypass valve. I will revert on the Grundfos training. Stefan will again explain to us the difference between the series connection as compared to the multi-stage pump. And I will respond on the issue of the performance of Grundfos pumps against other brands mentioned here. So Stefan, if you can maybe handle the question on the bypass valve, how does it work?
Anthony, maybe since I covered that part, so
no problem. Yes.
If you can allow, Stefan, if you can allow also, I will try to explain the bypass valve part.
No problem.
Okay, I will try to go back to the slide. Yeah. See, in the bypass valve, what we are trying to do is, we know this flow and head curve, right? So when the flow increases, the head comes down. Or when we increase the head, the flow comes down, right? So that's what we can see from this performance curve. So when we go towards right-hand side, we are getting more flow. The Q is increasing, but the head will come down. When we move towards left-hand side, it happens the other way around. So we reduce the flow, but we increase the head. So here is our duty point, original duty point, the blue square one. So here, what is happening is the system head is more. more than what is required by the system. So for example, the system can handle a maximum head of say 55. So we are not allowed to have more than 55 meters or 5.5 bar in the system. But as per our duty, we are having 70 meters, which is 7 bar, which is not good for the system. So how do we reduce the head? So in this case, what we do is we use a bypass valve. So we install a valve just parallel to the pump. So we are connecting the valve parallel to the pump. So when we open this valve, the system resistance will come down because this is closed. When this valve is closed, completely closed, we have some X pressure and it is going directly to the system. When we suddenly open this, the pressure will drop because we are reducing the resistance. When we open, we are letting the water to again come back to the pump. So what will happen is the duty point will shift from this point to the modified duty point. So the pump performance will move towards right hand side. So when it moves toward right hand side, means the flow will increase, but that flow will not go to the system because that flow will come back to the pump and it will be keep circulating. This additional flow of 21 meters will be circulating in this bypass line. But what is happening to the pressure? We are reducing the pressure from 70 meters to 55 meters, which is what is required by the system. So the system will be healthy. On the other hand, we are also managing the excess flow by not letting into the system, by just circulating in the bypass line. Hope that answers the question.
Okay. I'll pick up the question on the training to individuals. Yes, we do offer this. We are beginning to, again, send out program for training. We are there is a lot of background noise. We are beginning to set out training programs, and you can reach out to us and send. So, for example, send me an email, and I can be able to share what trainings we have in the future, which then we can share with you to join in. A lot of the trainings now are done online, so it's easy for you to join wherever you might be. We will be sharing our contacts for you to reach out to us. I think Feroz Stefan, someone was to come back to us on the difference between the series connection and a multi-stage pump.
Yes. Thank you, Anthony. I think I'll cover that one. In theory, when you look at a multi-stage pump, you've got a lot of different stages or impellers in series, and theoretically, it's the same as connecting two pumps in a series connection. The difference comes in is sometimes that you already have existing application, you already have a pump installed, and you don't want to change the pump altogether. And in some applications, it's just easier to add another pump in series to increase the pressure. But in all essence, when you look at a multi-stage pump, the impellers are running in series because you get additional pressure per stage that is installed in the pumping unit. I hope that answers the question.
Okay. Then the question, I think I'll take up the next question, which is the difference between the efficiency or performance of Grundfos pumps versus other pumps. From an engineer's perspective, this is largely the efficiency of a pump first starts off from the correct selection. If you select a pump that will generally operate at its highest efficiency, then you have a good solution. But if you have to decide between several manufacturers or several offers, the best way is to first understand how your system is working. How do you get the best efficiency? What's the flow and pressure you're looking for? And then use the manufacturer's data. And as we have shown on the presentation, you not only need to consider the efficiency, which is often printed by manufacturers, showing P4, you actually need to consider this complete unit. What is the efficiency of the motor? What is the efficiency of the pump? And what is the efficiency of that unit as combined? So you will get that a number of manufacturers are able to issue you with ISO certified performance curves. So you're able to actually tell, for this specific duty, am I running at the best efficiency for this unit? And generally, by availing these tools to you, for example, from Grundfos, you can go online and select from our Grundfos Product Center, and you can be able to, again, I presume, even from the other manufacturers, be able to get these data and to make a fair comparison. I cannot tell you on a flat answer whether what the difference is in terms of performance. But the information from today's training and from the manufacturers can help you make that decision on a project-to-project basis.
Thank you, Anthony, for your diplomatic answer. I think maybe I just need to add something about series and multi-stage. In the design of a pump station, it is possible that there could be other limitations, like say you want a pump that will do, the system is such that what the head is 400 meters. Now with 400 meters, it means you are going to deal with a pipe that would be more expensive than if you are using a lower rated pump. I mean, a lower rated pipe. So in that case, it may be wise, depending on all the economics involved, to have, instead of having a multi-stage pump that does 400 meters at one go, it may be wise to have one doing 200 meters and then another one doing 200 meters further ahead. That is just one example. The other thing that you may have to consider is that when you set up a new pump station, there are other costs that are associated with it. It could be the cost of building the pump station housing, and it could also be the cost in terms of operations, in the sense that when you set up a pump station, then you need also to hire staff to man it and also probably to secure it. Thank you very much. I think we will then take the next 5. There's someone who has asked if there is a specific line for geothermal pumping. I don't know whether you've seen it, Anthony. There's a very interesting question on geothermal applications. And then there is the question on the frequency of maintenance for a submersible pump.
Yeah.
Then the other one is, does steam pumps operate on the same principle as normal water pumps? The fourth one is it okay to use a concentric reducer on the suction side? And the other one is, what is the importance of motor reserve power? I think, Anthony, you can handle those, then we see if we have time again to look at others. I can still see we have a bit of time.
Okay. My colleagues, who will handle the issue of motor reserve power?
I think I can handle that one.
Okay.
Anthony, yes, the reason why you select or size a motor with reserve power, because you're most probably not going to have your pump just run at a specific point. Let's say, for instance, you have a system installed and pump is sized for a specific duty point with no access power allowed in the motor, and somebody, for instance, opens additional valves in the system, which pushes up your flow rate, and that can cause your motor to overload. So it's always important to have a safety factor in your motor as standard, because if you start running off the curve or off the duty point at a higher flow rate, your motor will overload and burn as a consequence. I hope that answers the question. It's just to prevent motor failure to a certain extent.
Yeah. Thanks, Stefan. I'll take up the question on whether we have a specific line for geothermal pump applications. We look at it from the problems that we are trying to solve in geothermal applications. Largely, those are to do with the chemical composition of the water that we are pumping. We find sometimes the water can be aggressive, corrosive to the pump, but also we are handling large, high temperatures, and sometimes we have grit in the water or abrasives. And yes, we have solutions selected on these bases, and we have supplied quite a number of pumps for geothermal applications. Largely, these are selected on the basis of whenever we find aggressive water, we will select a pump that can, whose material can be able to handle these, mostly high-grade stainless steel and titanium as materials. Or when we find high temperature applications, we again select pumps where we find a way of cooling the components and largely the motor to be able to pump the hot water. What we've achieved so far is that in some instances, we found 60, 70 degree water, and we have been able to pump this with submersible pumps. When we experience high temperatures for surface applications, that is not a challenge. Generally, for water, we can be able to pump between anything from 140 up to 180. So again, it's not a challenge for water pump applications. With grit, again, we have solutions where the pump is able to handle water containing solids. It's a bit general, it's not a specific line. We approach each problem presented by geothermal applications and find a solution for it. I think, I don't know if any of my colleagues can take up the question on steam pumps, whether they operate on the same principle.
I think Feroz would be the better person to answer, but I don't know of any steam pumps that operates the same way as a centrifugal pump. Because with a centrifugal pump, when you get air into your system, it generally causes cavitation. And with steam pumps, it generally means a lot of air in your system. So we mainly focus on water and clean water pumping applications.
Yes, I agree with you, Stefan, because we don't want, at least I don't want to misguide, because steam is something we don't handle, because steam is actually compressible, like means fluid. So the ones that we handle are the water. So to put it in other words, we are not the right people to answer the question.
Okay, there was another question regarding frequency of maintenance of borehole pumps. And when I look at the actual question is how long should a submersible operate before being serviced? And Patrick Chero here states, in most cases, we wait until breakdown. Yes, that has been a practice in our markets, but when we take a planned maintenance approach, generally the pump can be monitored for efficiency. How this is done is, first you need to check that if you have a flow meter, that then you can check if the pump is consistently giving you consistent flow. And when that flow begins to drop, it's a good time to lift the pump and check it, because it could mean, it could also mean that the pipe work is corroded, there is leakage back into the system. The other way to check this is when the pump components are worn, you begin to lose efficiency. When you lose efficiency, the pump power consumption begins to increase. So if you have if you have been monitoring the current that the pump is drawing, you are able to tell, well, my power consumption is beginning to increase. It's time to actually take out the pump. Even if the pump has not failed, you can see that maybe your power bill is beginning to increase. So largely by using the controls that are on the ground, you can be able to see what the status of your pump is, and then determine when to lift the pump out for service. Engineer Teo, I don't think I got the last question.
Yeah, the last
concentric reducer.
Concentric reducers on suction pipes.
Anthony, if you don't mind, I think I'll answer that one.
No problem.
Some of the biggest concerns when it comes to the suction side is getting an air pocket or high spot within your suction line. You don't want air in your suction line, and that's one of the reasons why they mainly use concentric reducers on your suction line, so that you have a flat surface on top and you don't get an air pocket in that suction line, which can restrict the flow rate into your pump and eventually have the air bubbles run into your pump's impeller, which can cause cavitation as well. So if you use a concentric reducer on your suction line and you can ensure that there's no air pockets developing in your suction line, it would be fine. But unfortunate part is most of your suction lines is generally alloy steel or something like that, or something similar. And then you don't always know if you've got an air pocket in your suction line. So in that sense, it's better to use an eccentric reducer, because then you know you have no high spots in your suction line. I hope that answers the question.
Okay, I think that is the second 5 answered. Anthony, I hope you are noting. There's the issue of critical factors for selecting submersible pumps for municipal waste water transport. Then the effects of exceeding maximum inlet pressure. Then there's the why pump fails to carry load when the suction is correctly sized. There's someone who wanted to know what would be the effect if you have 2 pumps connected. I think he meant in parallel, although he wrote in series, and one is much, much bigger than the other. Then there's the colleague who asked about the method of dry run protection. Maybe we can handle those ones again first, and then we see.
I think I'll take on the first one, and unfortunately I might not be able to give a straight answer for the critical factors for selection of wastewater transport applications, but it's something we can answer on email, though on our series of trainings, because wastewater is a large field. We actually have a session that we have planned for selection and sizing of wastewater pumps and transport of wastewater. It's a complete session on its own. So maybe that is something we can be able to do. If the participant has a specific site, then he can email me directly. But wastewater selection is a bit of an extensive topic that we have planned to cover. My colleagues, if you can answer the issue about exceeding the maximum pressure on the inlet to the pump.
Yeah, Anthony, I will answer that question if you can allow me.
Yes.
So actually, any pump will have a limitation on the maximum inlet. So it's mainly based on the mechanical seal, because the mechanical seals will have limitation on how much pressure it can handle. And also, it depends on the differential pressure. Means, for example, if the pump develops, say, 20 bar pressure, okay, and then the pump's maximum pressure that it can handle is say 30 bar, then the inlet pressure will be limited to only 10 bar. Because if we get more than 10 bar, if the pump is developing 20 bar, then we will have a total pressure of 30 bar and more. Means we are exceeding the maximum operating limit of the pump. So the weak parts like mechanical seeds, the air vents, so all these spaces are the most prone areas to leak, and also where we have the gaskets. So that will start leaking. So this is why we have to restrict the inlet pressure. So we should not allow the pressure on this section to increase beyond what has been recommended by the manufacturer. Hope that answers the question.
Okay. Stefan, will you come back on the effect of having two differently sized pumps? I think we can consider both in series and in parallel.
Yeah, like I said, in series, I kind of agree, because you want to increase the pressure and have it at a similar flow rate. So you're going to overpower either one of the two pumps, and then basically use the one pump almost as a valve in your system and use it to absorb additional pressure and friction losses. So I wouldn't advise doing it in series. When it comes to parallel, it's going to be based on your system design. So if the pump and the pipework can compensate for the amount of flow, it can work, because one's just going to allow the additional flow rate into the system. When it comes to the pipework and the construction, because your flow velocity, etc., is going to go up, the one pipe is just going to overpower the other pump. So it's basically not going to be able to force the water into the system, given that it might not be running at the same pressure rating. So when it comes to a parallel connection, like I mentioned in the presentation, it's important to have them more or less at the same duty point and the same flow rate, so they can achieve the same pressure rating at the same flow rate, and therefore you'll have double your flow rate theoretically at the same pressure level. However, we do see these in a lot of applications with jockey pumps. So the reason they connect a jockey pump in a parallel system is for your low flow operation systems. But this will be based on the MCC that you actually have on site. At low flow conditions, just the jockey pump will kick in and operate on the low flow conditions. And as soon as more or higher flow rates are required, the other pumps or the bigger pumps will then kick in a cascade type of operation and operate, switching off the jockey pump in the system like that. I hope that answers, because I think that's what it was leading to, is more or less on the basis of a jockey pump.
Okay. I think what has not been answered is why pumps fail to carry load when suction is correctly installed.
And I think that question leads directly, excuse me for jumping on the question, directly, doesn't manage to carry the load or carry the water. So, for instance, I've seen a lot of installations where it almost hunts, where it picks up the water and then drops it again. And it mainly falls back to the last topic that Feroz discussed, which was MPSH. It means the MPSH required by the pump that is not adding up to the MPSH available on site. So most cases, you just need to go and double check what the MPSH available on site is and make sure that it matches to the requirement of the pump.
Okay. Fine. I can see we still have some time. There's the colleague who wanted to know the relationship between pump inlet, impeller size, outlet, and what is the effect. Then there's a colleague who wanted to know how do we test functionality of DC submersible pump drive. There's a colleague who wants to know the installation status of digital smart pumps in Kenya. And there's a colleague who has just asked what is the highest ATEX zoning for Grundfos pumps. In particular, they would like to know if we have zone 0. We can handle those.
I think they came in too fast. I'm trying to just get them.
Okay, and we can go one by one with the relationship between pump inlet, impeller size, outlet, and what is the effect. I guess it's the effect of varying this. Then there's the issue of how do we test the functionality of DC pumps? How do we test functionality of DC submersible pump drives?
Okay.
Yeah.
Okay. Anthony, maybe I will take the first question. Do we have any relationship between the pump inlet, impeller size, and outlet? To be honest, no, there is no relationship between the impeller size and the inlets, because in some cases, like the end section pumps, the impeller dia will be quite larger compared to the inlet size. But when it comes to borewell pumps, where we have to fit into 6 inches and 8 inches, the ratio will be different. So there is no fixed ratio between the inlet outlet size and impeller size. So I think we have answered that question. So the next one.
Testing functionality of DC submersible pump drives.
Functionality of the drives. Stefan, do you like to say something? Yeah.
I can jump in there, Feroz. I think it's going to be based on whether or not the drive is AC and DC compatible. So I know often to test the functionality of a drive in anyone's workshop, they don't necessarily have enough DC supply or solar modules installed to be able to test it on a DC supply. But if the inverter or the DC drive has AC functionality, so you can connect it to a normal grid connection, that is usually the best way to test it in your workshop, is by using an AC connection to test the functionality. Obviously, you'll have to connect it to a pump and then run it on a test bed to best see the outcome of the testing, just to simulate the operation. But you're doing it on an AC connection or a grid connection instead of a DC connection. That is if the drive has the functionality to run on AC. If it's only DC, then the unfortunate part is you're going to need a big enough DC supply to be able to take functionality.
The next one is installation status of digital smart pumps in Kenya, and if at all you have any specific examples.
I'll try to understand. Yeah, I'll try and understand the digital smart pumps being referred to. Yeah,
Anthony, sorry to interrupt. So before you answer, I just have one request. So we have a feedback form because we have series of training. So it'll be good to get some feedback. So as we reply the questions, I will just share my screen where participants can scan and give their feedback. And also I will post in the chat box of the link. Sorry, Anthony, you can continue.
No, thank you. Thank you. Just to understand the digital smart pumps is that we have a wide range of these solutions. Largely, we've done a number of projects specifically in building services, where we have solutions that are able to communicate directly with our remote units. We've also done some bit of work with Guru Water, where we are able to monitor their pumps, or rather they are able to monitor their pumps online and be able to detect faults online remotely for boreholes that are located in various locations. So that has been something that we've done with them. But we also have a few of our clients who install digital control units. And again, with these, we have quite a number of solutions that can be offered, specifically with drives. Other digital solutions we offer are for dosing of chemicals in water treatment. So again, we've done some bit of work with the Nairobi Water installations at Nyedu, but we also have a number of industrial customers, specifically the breweries and the bottling companies. They also use these digital pumps for dosing of chemicals in their cleaning applications. So yes, we have a number of examples of these digital smart pumps that we are using in quite a number of locations.
Okay. Highest ATEX zoning.
I don't know if any of my colleagues can remember the exact rating that we have, but generally we look at it from the application point of view. We have pumps that can be used in explosive environments, in environments where you don't want any arcs or sparking in the pumps. But basically, these are with specialized motors that have zero risk of generating sparks. So we often approach this from the problem side of this, and we can be able to, the customer just needs to explain to us what is in the air that they think would cause this risk of a pump starting a fire or explosion, and we design a pump to that sort of a requirement.
Okay. I'll just be shooting them now, Anthony, and we move.
Yes.
I can see Alex Wahome has raised his hand. I think I want to give him a chance, but there's the colleague who has asked what makes Grundfos RSIS more expensive than other brands. And there's David Njeru would like to know if an inducer is introduced at the impellers, would that reduce cavitation? And what would that affect the operating ranges, including efficiency? Then we'll allow the colleague who raised his hand to speak.
Okay. I think the product being referred to here, the Grundfos RSI, is an inverter that is used to convert DC power supply from solar to AC that can be used for pump applications. Now, it's sometimes difficult to answer a question of price without knowing what we are comparing it with, but I'll try this. Our inverter comes with a number of pump-specific functionalities. For example, being able to determine when it is safe to run a pump, when it needs to slow down the pump, and also how it can draw the maximum power supply from the mains, so that by using this sort of inverter, you are able to use the available power to the best efficiency of the pump. Sometimes you'll find that maybe what the customer requires is less functionality, and the best thing is to communicate that to us, because we have other solutions that are lower cost. So for example, we also have pumps that have an integrated inverter inside it, so which means you don't have to buy an inverter. We also have inverters with less functionality but high efficiency. So again, it often depends on what the client is looking for. In some instances, we give the RSI because of the higher functionalities that are available within it. But sometimes if those functionalities are not being used, then maybe we've sold a product that has more features than are required. So that probably would answer the question of this cost of the inverter.
Anthony, can I add a line on the inverters? The reason why, what we have found in the market, the reason why our RSIs are more expensive, exactly as you have explained, it is because what we have seen in the field is users would buy an inverter from elsewhere, but then have to invest in additional protective features of the pump. But then RSI is complete, as Anthony said. RSI is complete with the full protection of the overload, overcurrent, over voltage. It also has the, you can also go into RSI and extract the performance of the pump. So it can give you the history. When did your pump begin to fail? So that's another feature which makes it a little bit more versatile compared to the rest. Also, it has got a capability to connect remotely. So from thousands of kilometers, you can easily interact with the an RSI inverter and get to know how it's performing. So that is why sometimes you find it coming at a premium price. Thank you.
Thank you very much, Hilary, my colleague.
Anthony, there's the issue of if an inducer is introduced in the impeller, would it be able to manage the issues of cavitation better?
Theoretically, yes. Practically, what we do is that we have solutions, and I think the general approach is when you have such problems, reach out to us, and then we can see how the installation is done. The point of an inducer, basically what we've done is that, for example, in boiler applications, we have pumps that are designed to have lower NPSH requirement on the first impeller. So it sort of works like an inducer because that impeller is designed differently from the other stages of the pump. So in terms of actual application, yes, we have found ways of doing that, but not necessarily using an inducer, but redesigning the pump inlet. And that is actually a solution that we are implementing with a number of boiler customers to be able to do that. So whenever they have these challenges, we can always reach out and we look at the calculation, see what we can be able to change and offer a solution.
Okay. solar-powered pumps, that is the one which has just come now.
Yes.
Someone has written, Jairus read, what makes centrifugal pumps more durable than vertical pumps? Jairus, I think there's a problem with that question. Maybe you need to make it better, because there are vertical centrifugal pumps, just like there are also horizontal centrifugal pumps. So maybe make it better, then the Grundfos team will handle it. In the meantime, Anthony, you can answer Samuel Obonyo, who is asking, are there provisions for solar-powered pumps? And what pump would you recommend to a small-scale farmer for irrigation? Okay, fine. Anthony, over to you.
Any of my colleagues to answer the question regarding solar pumps? I'll actually pick the issue of centrifugal pumps being more durable than vertical pumps. If my understanding is correct, is when quite often when our customers talk of centrifugal pumps, they're talking of the horizontal cast iron single stage pumps. That compared to vertical stainless steel pumps. On the issue of durability, you'll find that the cast iron pump is basically designed for raw water pumps with a lot of material that even if with wear, even if the actual casing itself is getting worn, it takes quite some bit of time. Whereas the vertical multi-stage pumps are largely designed for high efficiency and for pumping clean water. So if you apply the vertical stainless steel pumps in a raw water application, because the design is made with very small clearances, then you will find that, yes, a lot of debris, silt and the like are likely to wear the vertical pump out faster than it would a horizontal centrifugal pump. Grundfos provides both kinds of pumps, and quite often it is selecting the right horse for the right race. So yes, mostly it's to do with selection. When selected correctly, the pumps will both run for a long time.
Maybe I can talk about the limitations of the solar powered, and it narrows down to basically the cost. Up to a certain level of the kilowatt size requirement, it becomes unreasonable to at the current prices of the cost of panels and the probably cost of land to lay those panels. So it reaches a point where when you calculate the payback period, it makes more sense to run on an electric system than solar panel. That is the current limitation. So it doesn't actually go to the solar pumps have no problem. The cost will be on the panels themselves and you may require acres of land, especially where the cost of land is going up. Thank you.
Yes, Hilary, also including that sometimes, just to add, people want to oversize the system to a bigger system than what is actually required. But if you accurately size the system based on your daily requirements with some safety factors, generally there's not really a lot of limitations other than what you said, the space constraint for installing the solar modules. But if the system is accurately sized and not oversized, you can always realize your return on investment.
I'll go to some slides and cross-check.
Good. As we are winding up, Anthony, maybe you just need to tell us if, I know we are in a market with very many suppliers. if somebody wanted to know the one reason why he or she should buy pumps from you, you could maybe just do your sales pitch as we are winding up. I know there are many questions still. Some we have not got because the screen was also moving too fast. So I'm sure we will arrange with you to answer them by email. But Anthony, you can give us that pitch for as part of our winding up.
Yeah, it's usually a tough one to make a pitch, a sales pitch to engineers. I think from Grundfos, what we strive to do is to work on wholesome solutions to the problems that our clients face. For this reason, we've developed Grundfos pumps, invested much more than any other company in research and development. But these solutions are not complete without the engineer solution, rather engineers input. There's a lot of background noise, sorry. Yeah, so thank you. So these solutions are not complete without the engineers' input. So we work collaboratively with engineers. You can reach out to us. We have invested in having engineers who can work with you through the design. And after we've supplied the pump to you, we also have a large group of service partners. So whichever part of this country where you might have a Grundfos pump installed, we can get a supplier, rather a service partner to support you in any county. And this, you do know, you can go to our various partners. They offer you solutions, not just supplying the pump, but supplying the complete unit. Now, once the pump is running, we also have our own service workshop and our service crew. So we again can support your product even with the after-sale service. I think that is our commitment to supporting all our customers. And we are always looking in terms of what can we do best for our customers. We are open to you giving us feedback. So we are here for you. I don't know if there is anything my colleagues would like to add. Though I would like to close this by checking on one of the questions here, and maybe someone can give me an answer. I saw it on the chat. There was the question of whether the human heart is a positive displacement pump or a centrifugal pump. I think part of what I will say is that I've seen questions asking which is the best pump. I would say if we are not number one, then the human heart is number one. So maybe that is a tough competition to beat.
Thank you very much. Thank you also for to all members for taking your time to attend this webinar. Just before I hand it over to Anne Dung for closing remarks, very well attended means that members have the interest to know more about pumps, which is a good thing. At one time, I noticed that we were a full 590 of us. I'm sure together on behalf of the Water and Sanitation Subcommittee, together with the IEK, we will be able to organize more of such. And also to everyone who attended, thank you, and for the engagement, the many questions, which meant that we were all concentrating. much as some of them were not answered, I'm sure we will get an opportunity to answer them in the future. Over to you, Madam Anne Ndung'u, for the closing remarks.
Okay, thank you so much, Engineer Dick Ndiayo. As you've been told, my name is Anne Ndung'u. I'm the Policy Research and Advocacy Manager. And I want to start by thanking Anthony Wachira for his support by giving us that support of Grundfos in organizing this webinar. We would not have had such expertise in organizing this webinar without him. I also want to thank our presenters, Stefan, Benta, and Feroz. Both of them have shown a lot of knowledge about an engineer. But I can see from the comments and from the questions that have been asked that it has been very engaging for both new and experienced engineers, and that we should organize more of these activities and webinars for members. And then finally, I want to thank the Water Committee for their support for these webinars. This is just the beginning of our partnership with Grundfos. It began during the conference last year and it will continue. So we can only say thank you to all these people and ask them to continue partnering with us in these ventures. Finally, I want to thank members for coming for this webinar and for your continued support. We will work on CPDU points and certificates so that you get them hopefully by the next 2 weeks. You should have them. And in case of anything, we shall be sending out the presentations and we shall be sure to make sure that we organize similar events. Thank you so much.
Very good. Thank you. And I think with those few remarks, we come to the end of our session. Engineer Chiang, are you there? Engineer Chiang, Chair of Water Subcommittee, you are there? Okay. I think we can call it a day. Thank you.
Thank you very much. Appreciate the time.
Thank you. Thank you from my side. Thank you, everyone.
Thank you. Thank you.
Have a great evening. Bye-bye.
Thank you for the presentation.
Thank you.
Thank you.
Thank you.